Everything. Hello everyone, I'm Silvia Franceschi and I'm from Italy, and I will present you the new L.E.S.T.O Toolbox. It is a toolbox for estimating forest structure and biomass through LiDAR data. So let me introduce myself before. I'm Silvia. I'm a co-founder of HydroloGIS with Andrea Antonello. You will see him in the presentation after mine on geopaparazzi. I'm an environmental engineer specialized in hydrology, hydraulics, and geomorphology. I started a PhD student this year on science and technology at the University of Bolzano in Italy, and I develop and participate to the development of scientific models contained in the S.r.l library of hydrology, hydraulics, and forestry. And since this year, I am also an OSGeo charter member, thanks to Vegetation for nominating me. So, HydroloGIS develops mainly environmental models, and we develop the S.r.l library. S.r.l library contains modules for vector and raster processing, geomorphology, forestry, mobile mapping support. It is the core behind the spatial toolbox of HydroloGIS, but it can be used also standalone in the application called Stage. It is the spatial toolbox and geoscripting environmental tool for environmental modeling. S.r.l contains different sections. The first one and the original one is the Horton machine. It contains different modules for dam elaboration, hydrology and hydraulics elaboration, network extraction, and statistic making. And then other tools for raster processing, more utilities for making edge detection, mosaics, and profile, and all stuff like that based on rasters. Same for vector processing. Tools for buffering, merging, converting different kind of vector data. And from this year, in S.r.l, we integrated also some mobile stuff. You will see in the presentation of geopaparazzi. We are mainly dedicated to the interaction between the library and geopaparazzi to convert the data for geopaparazzi and coming from geopaparazzi. And the last one section is the L.E.S.T.O toolbox, and it contains some tools for analyzing LAS data, LiDAR data, and extracting information about vegetation. L.E.S.T.O is for LiDAR Empowered Science Toolbox open source, and in this presentation I will focus on the tools contained in this package. So L.E.S.T.O is an open source GIS-aware library dedicated to sciences that make use of LiDAR data. It is developed and maintained mainly by HydroloGIS and the team of Professor Tonone at the Faculty of Science and Technology of the Free University of Bolzano in Italy, and it contains tools for handling high-resolution LiDAR data and for LiDAR analysis related to forestry. There are different sub-packages inside L.E.S.T.O. We have some utilities and filtering tools. Then we have raster tools for interpolation and calculating digital terrain model, digital surface model, and canopy age model, and some other tools for the extraction of building, forestry analysis, and intensity analysis. This is an overview of L.E.S.T.O in the application stage. As you can see there, we have all these, the main package is L.E.S.T.O, and then we have the sub-packages, utilities, building, raster, vegetation, filter, and flight times. And then this is a graphical interface that is automatically created by the stage application. And for each module, you have the graphical interface, and also in the tab you can, below here, you can also choose the description, and you have a short documentation of the modules. So let's start with seeing some of these modules. We start from the pre-processing tools. The pre-processing tools are mainly contained in the two packages that are utilities and filtering. The very first module we use for LAS analysis is the indexer, LAS indexer. It creates the indexes for LAS files. It is very simple. Indexes helps in our elaboration to speed up the elaborations. It is very easy. It requires an input, the folder. It can work on a folder or on a single LAS, and then just the names and the projection, and then you can you will obtain a new file that is the index of the LAS, like for the shapefile, and a general index for the folder if you are working on a folder. The second tool is the LAS info. It prints out the information of LAS file or folder, and it is very easy. You just insert the file or the folder, and in the console there are all the information related to this, the general information like the boundaries, the ranges, and the projection, and some other stuff here. So you don't have to read all the LAS, and so this is very quick, and you have all the information you need to start to analyze the LAS. And then we have another tool that is very helpful for creating overview of the LAS files. And it creates a shapefile with the overview. Just put in the information required, the LAS folder, and this is the result. And the shapefile contains as attribute the name of the LAS file, so you can quickly understand which is the LAS you are interested for your analysis. Then we have the last point density extractor. This creates a shapefile with the point cloud density on a given grid, and it is very easy. This is the graphical interface, but and here we have the result. As you can see, this is a map of the colors are from white to dark gray, increasing the number of points for each cell. You can decide the size of the cell here, and we do the square region. And as you can see here, even if the companies, the LiDAR companies, assure an average number of points per square meter, there are very many differences also in neighboring areas. So here we have very few points per square meter, and here many. Sorry. And then we have some filtering algorithms. The first one is the last height distribution. It analyzes the height distribution and categorizes the forest type. This is very helpful if you do forestry. And it gives us as output this chart containing the height distribution with the number of points with the same height. And the original curve is the red one, the interpolated one is the blue one, and the second derivative of the interpolated is the black one. When there are changes in the sign, positive and negative, of the second derivative, you have different layers of vegetation. So at the same time, a map of the vegetation structure is created, and you have 0 where there is no vegetation, 1 where there is a single layer vegetation, 2 means a single layer vegetation with 2 different levels, and 3 is a multi-layer. As you can see here, we have the dots. The dots are the mapped trees from the field survey. As you can see here, well, we have only the result of the vegetation structure is very coherent with the map, the field survey, because where we have high and small trees, we find the 2 layers of different vegetation. Here we have only 1 layer of vegetation, and where there are big trees, it is possible that there is a multi-layer vegetation, because there are the big trees and also the small trees underground. Then we have a last histogram. It creates the histogram of the point in the last file, and you can choose here if you want to use the intensity, the histogram of the intensity, or the histogram of the elevation. And this is a result of the histogram of elevation of an entire L.E.S.T. It is very interesting to understand how the vegetation is distributed inside a L.E.S.T. And then a L.E.S.T. merger that merges all the L.E.S.T. file contained in a folder in one single file. There is nothing special in this. And then a L.E.S.T. thresholder. It extracts the point with values in an interval, and you can put the lower threshold and the upper threshold, and then you can choose if you want to work on intensity or elevation. And okay, the result we will see as histogram. This is the histogram of the intensity of an entire L.E.S.T. It has 4 bins full. And the histogram of the threshold L.E.S.T. is much more thin, because we extracted only the values in this interval. This is all about the preprocessing. Then we have some raster tools. Raster package contains all the available tools for interpolating and creating a raster from a L.E.S.T. And we have different type of interpolation to create digital terrain model and digital surface model. For example, we implemented the adaptive thin filter of accessons, and then we have another function that is a bivariate raster interpolation, or an inverse distant weight method. And then there is also the possibility to extract the maximum or minimum value of the elevation in each pixel of a raster map, and also to create the so-called true DSM, that it is a triangulation of the DSM, of the point cloud, the very upper point cloud. This is an example of the interpolation of the digital surface model using the adaptive thin, and here is the grid of thins used. And this is the interpolation using the maximum height for each pixel. As you can see, where there are white pixels, it means that we don't have any point, any raw point, cloud point in these pixels. So it also helps to understand how good are the data you have. We dedicated a section to buildings, but unfortunately now we have only one tool to extract the building from L.E.S.T. But we hope to go on with this, also with these tools. This simple simple tool is called L.E.S.T.O DTM Building Extractor, and it is based on the identification of the holes in the ground generated by cutting all the points with an elevation over a given threshold. And the output can be also cleaned and smoothed to obtain better results. Here is the graphical interface. It requires very few parameters, and then the result is this one. As you can see, the blue polygons are the first extraction, and then the red polygons are the filtered and smoothed buildings. As you can see in this part, we almost found all the buildings present. But in the blue one, there is also some refuse of vegetation, big trees, and so on. And then we decided also to have a section dedicated to flight lines, because flight lines inside a LiDAR survey are very important. On flight lines, the intensity depends mainly on the flight line. So we decided to have a tool to split a single L.E.S.T. in different flight lines, and so it creates different class. As in this case, based on this histogram of the times inside a L.E.S.T., we will split each of these sections in different L.E.S.T. This is an example of the effect of the flight lines on the intensity values. The intensity value depends on the direction and on the height of the aircraft. So using the same map color, the intensity values here are higher than the ones in this other flight line. And so we also developed a tool to normalize these kind of situations and to obtain a normalized intensity value over an entire L.E.S.T. Unfortunately, I couldn't do a screenshot because I forgot all the things at home, but I did an histogram to show you that before we have different values of intensities, and then the normalized one has only as few categories of intensity, so they are normalized. And then we arrive to the vegetation section. There are two different approaches to extract the vegetation from the LiDAR data. One is the area-based approach, which means that we estimate all the parameters generally and statistically for an area. And then the other one is the individual tree approach. That means that we extract the information of a single trees from a L.E.S.T. data. We work mainly in this with this second methodology to extract the single tree information, position and information from LiDAR data. Okay. This position and vegetation of this position and information about the trees can be used to characterize the forest structure, to calculate the volume of the biomass, and also to help us to identify the hydrogeomorphological hazard related to hill slope stability and transport of woods in rivers. We are testing these modules on a study area in Italy, very north of Italy, here at the boundary with Austria, in Aurina Valley. It is an area of about 10 square kilometers, characterized by a high local variety in forest structure, mainly composed of Norway spruce, but with some large and stone pines. Our LiDAR survey is of 2012, and we have almost all the products, DPM, DSM, and last point, raw point data at a density of 10 points per square meter. We did a field survey in the summer season of 2013, and we mapped all the trees over 12 circular plots of a radius of 15 meters in a buffer of the roads of 150 meters. And we have different forest structures, young, biplan, adult, and multi-layers. We mapped all the trees, as you can see here, and we also took information about the diameter, the height, and the species. And based on this, we derived some allometric relationship to relate the volume to the height and the diameter of the trees. These are some information about the trees. These are the number of the trees in each plot. And this is the volume of the trees in each plot. And here the average height of the measured trees for each plot. So, the available method that we have now in L.E.S.T.O are the very base method, very simple method. The first one is the raster maxima finder, and it identifies the local maxima from a raster input data. This is the graphical interface. It requires the threshold over which you want to extract the trees, and the radius to have the maximum. And the output is the shapefile of the extracted trees. As you can see here, we have the triangle. The green triangles are the mapped trees from field survey, and the circular, the blue circular, are the extracted one. So we mapped only, the field survey is only inside the plot, but the elaboration is also outside. As you can see here, we missed a lot of trees. And here we have also a simplification of the crown with the circles. But if you change the parameters, you can see that here we have much better results. We miss only six, I think, trees inside the plot. And this is a very rough delineation of the crowns. Similar to the raster maxima, we have the point cloud maxima finder. It has another algorithm, but it is always based on the identification of the local maxima in the point cloud input data, and also requires some information about the threshold on the height and radius of influence. And again, the result is a shapefile with the position of the trees and also the height. In this case, also we miss some trees, but if we work on the radius, we can more or less find all the trees in the plot, with also the height as an attribute. And then we have the last tool, it is the Watershed algorithm, and it is used to delineate the crowns based on the Watershed algorithm. It's based on a canopy 8 model reversed, so you have concave canopies instead of convex canopies. And here you can see the crowns delineated in blue. The other circular are the simplified one. So this is almost all about the what we have in L.E.S.T.O. Our future plans is to stabilize and release some of other tools we already developed of pre and post processing of the results of the extraction of the trees to improve the general results. We also implemented a particle swarming optimizer for calibrating the models on the test area and then using these parameters to the general area. Then we want to integrate a visualizer of the last point data in the stage, so you can briefly visualize the data also. And last, we will use the results of this extraction, the vegetation, the position of the trees and the height, to integrate in some models of flooding to understand the relationship between the presence of wood and the transport of wood during floods. L.E.S.T.O is developed by us and released under open source license GPL3 on the JGRAS Tools website, and it is open to the contribution of also other. If you are interested to contribute, we are very nice to put your models inside the tool. And these are some useful links where to download the JGRAS Tools stage and UDIG if you want to use it in UDIG. And here is a picture of our Dolomites in Italy, because all the others have pictures and my presentation was a bit boring, so I decided to insert this picture. Thanks you for the attention.
Silvia さん、ありがとうございました。シルビアさんの発表にご質問なかったらどうぞお願いします。
Thank you for your presentation. Very interesting.
Thank you.
Unfortunately, I didn't using the LiDAR data,
okay.
But now I try to using the UAV. Unmanned aerial vehicle, and we can obtain some kinds of crowd point data.
Okay.
Yeah, so that if you know any example to analyze crowd point data from the UAV using LAS
okay.
applications.
Sorry, but about my ignorance. But there are also information about height in this
yes.
crowd.
Yes.
Height, intensity, maybe? Or
no, unfortunately not. Just only the XYZ. So that we can obtain the DSM models about for the landscape, but there is no intensity details.
Okay, but it is a point cloud. It is not. Okay. So I think if you can convert it into a LAS, it is not a complete LAS, so you cannot use intensity and so on. But the other tools can be used at the same time, I think. But does this sensor have different return impulse or just one? So if you have vegetation, you have
almost the surface of the vegetation.
The surface, okay. Yeah, you can use it. It is they are a bit simplified respect to the LiDAR, but you can use it also for Maxima Finder. Yes. Some of these tools work well in the first pulse. That is the same as the data you have.
Do you have data here?
Unfortunately not.
Okay, sorry.
Thanks, Silvia.
Thank you.
Thank you so much. ありがとうございます。